This is section 4.1, extreme values of functions on closed intervals. One of the most important applications of the derivative is its use as a tool for finding the optimal or best solutions to problems. For example, what is the shape of a can that minimizes manufacturing costs? We can apply derivatives to find maximum and minimum values of functions and extend this idea to different applications in calculus. Let's talk about absolute maximum and minima. Our discussions begin by looking at functions defined on an interval. Let C be a number in the domain D of a function f. Then f of c is the absolute maximum on D if f of c is greater than or equal to f of x for all x in the domain D. It's the absolute minimum on D if f of c is less than or equal to f of x for all x in the domain D. An absolute maximum or minimum is sometimes called a global maximum or minimum. The maximum and minimum values are called extreme values of f. We will illustrate this using the picture below. The figure shows the graph of a function f. I'm going to label some x values on the graph. A, B, C, D, and E. So now the function f has an absolute maximum at D. So this is the absolute maximum, and it has an absolute minimum at point A. Note that the point D, f of D, is the highest point on the graph, and the point A, f of A, is the lowest point on the graph. Local maxima and minima. The number f of c is a local maximum of f if f of c is greater than or equal to f of x when x is near c. It's a local minimum of f if f of c is less than or equal to f of x when x is near c. In the definition, we say that something is true near c if it is true on some open interval containing c. Generally, we're looking for peaks and valleys of the graph. Let's illustrate this on the picture above. Looking back at the graph, if we consider only values of x near b, for instance, if we restrict our attention to the interval a to c, then f of b is the largest of those values of f of x and is called our local maximum of f. Likewise, f of c at this point here is called a local minimum of f because f of c is less than or equal to f of x for x near c, for example, in the interval b to d. The function also has another local minimum at e, so f of e is also another local minimum. The graph below illustrates how to identify types of maxima and minima for a function with a domain where x is between and inclusive of a and b. Notice when x equals a, we have an absolute minimum, or we also, instead of absolute, we might refer to it as a global minimum. There's a local maximum when x equals c, a local minimum when x equals e, an absolute maximum or a global maximum where f equals d. And notice that at this point, the function, the derivative, f prime, is undefined when x equals d. And finally, there's another local minimum where x equals b. So at this point here. So what can you say about f prime of x at all the local, relative, and global extreme values? Well, what we can say is the only places where a function f can possibly have extreme values, local or global, are at interior points where f prime equals 0. So in this case, at the points, if we look at the graph above, that was when x equals 0, and x equals c and x equals e. Also at interior points where f prime is undefined. And we saw that when x equal d above. And finally, at endpoints, can't forget the endpoints of the domain F. And in this case, that was x equals A and x equals B. All right, so a critical point is an interior point C in the domain of F at which either f prime of C equals 0 or f prime of C does not exist. So note that it's a point, so we has two coordinates, an x coordinate and a y coordinate, and that you might need to find both of those coordinates. For example, if you are doing implicit differentiation, you'll need both the coordinates of the critical point. So let's look at an example. The first example, we want to find the critical values of the function h of x, where h of x equals x divided by x squared plus 1. So the first thing you want to do to find those critical values, take the derivative and set it equal to 0. Before I do that, I have h of x equals x squared plus 1. I'm going to rewrite my function h of x. So instead of using the quotient rule, I can use the product rule to take the derivative. So I want to find h prime of x. And in order to do that, now I have it set up with two functions that are being multiplied together. I'm going to call my f is going to be x, and f prime is the derivative of x, which is just 1. And my g is going to be x squared plus 1 to the minus 1. So g prime is negative x squared plus 1 raised to the minus 2 times, I have to use the chain rule here, times the derivative of what's inside the parentheses, which is 2x, and derivative of 1 is just 0. Now I'm going to cross multiply, so h prime of x equals f times g prime, so that's x times negative x squared plus 1 to the minus 2 times 2x plus f prime times g, which is 1 times x squared plus 1 raised to the minus 1. I can simplify that a little bit because I have an x times 2x, so that's going to be 2x squared, but I have a negative sign, so I need my negative there. X squared plus 1 raised to the minus 2 plus x squared plus 1 to the minus 1. So I've done my first step, which is taking the derivative. My next step is to set it equal to 0 and solve for x. I'm going to add 2x squared times x squared plus 1 to the minus 2 to both sides. So I end up with 2x squared times x squared plus 1 to the minus 2 equals, and I still on the right side have my x squared plus 1 to the minus 1. I'm going to rewrite these equations so that I don't have my exponent. So I have 1 over x squared plus 1 on the right side. And on the left side, I have 2x squared in my numerator and x squared plus 1 squared in the denominator. Remember, the negative exponent just means it's in the, it's 1 over that. Okay, so now I'm going to multiply both sides by x squared plus 1 squared. So I can get rid of my rational expression here. So the left side cancels and I'm just left with the 2x squared. On the right side, the denominator cancels, but with only 1. So I still have x squared plus 1 left in my numerator. Now I'm going to solve for x. So I'm going to subtract x squared from both sides. So I end up with x squared equals 1. If I take the square root of both sides, I end up with x equals plus or minus 1. So I have the x value. My next step is to find the corresponding y value, and I find the y value by substituting the values of x back into my original equation. So I need to find h1 of 1. So x over x squared plus 1 equals 1 over, wherever I have it next, I'm going to substitute in the 1. 1 squared plus 1, so I end up with 1 half. So my first critical point is 1 half. And then my second critical point, because I ended up with plus or minus 1, is the negative 1. So I'm going to substitute that back into my original equation, and I have negative 1 divided by negative 1 squared plus 1, which is negative 1 over 2, or negative 1 half. So my second point is negative 1 half. So my critical points, I have two of them, are 1 half and negative 1 half. All right, now we're going to talk about the extreme value theorem. The extreme value theorem states that if f is continuous on a closed interval ab, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d on the interval ab. The extreme value theorem is illustrated in the graphs below. Note that an extreme value can be taken on more than once, as we see in the graph on the far right. We have C1 and C2, which are both absolute maximums on that interval. Note that if a function is not continuous and or not defined on a closed interval, then we cannot guarantee it will have an absolute maximum or minimum. The local extreme point theorem says that if f has a local maximum or minimum at x equals c and f prime of c exists, then f prime of c equals 0. Note that the local extremum implies f prime equals 0 there, but not the other way around. For example, consider y equals x cubed at x equals 0. I'm just going to sketch a graph of y equals x cubed so we can see what that looks like. So that's my graph of y equals x squared. If I take the derivative, if I find the y prime, well, that's going to be 3x squared. And if I substitute in 0, I get that, let's just call this f prime of x equals 3x 0, and f prime of 0. If I substitute in 0, I'm going to end up with 0. So in this case, there's no local extremum for f of x. So just because the derivative equals 0 doesn't mean we're going to have an absolute or local max or min. And that example is showing you that. Okay, so what is the strategy for finding our maximum and minimum on a closed interval? Well, the first thing is we assume that the function f is continuous on the closed interval ab. Our first step is to find all critical points in the interval where f prime of c equals 0 or where f prime of c does not exist. Our second step is to evaluate f at those critical points and at the endpoints of AB. Then step 3 is to take the largest and smallest of these values from step 2 for the absolute maximum and minimum values respectively. So let's do some examples. We want to find the absolute maximum and minimum values for the following functions in the given intervals. So the first example is f of x equals x cubed minus 3x squared plus 1 on the interval negative 1 half to 4. So our first step is to find all those critical points in the interval. So we want to take the derivative, find f prime of x. So the derivative of x cubed is 3x squared. The derivative of negative 3x squared is 6x, and the derivative of 1 is 0. I can simplify this a little bit by factoring out 3x, and I end up with 3x times x minus 2. So I want to set this equal to 0. I'm going to set f prime of x equal to 0. and solve for x. So when does this equal 0? Well, when 3x equals 0 or when x minus 2 equals 0. So 3 times x equals 0 when x equals 0, and x minus 2 equals 0 when x equals 2. So I found two critical values. My next step is to evaluate the function at these values. So I'm going to plug in 0 to my original equation and see what I get. So 0 cubed minus 3 times 0 squared plus 1 equals 1. So the first point I have to evaluate is 0, 1. Next, I'm going to substitute in my second critical value, x equals 2, back into my original equation. So I have 2 cubed minus 3 times 2 squared plus 1. And when I do that, I end up with negative 3. So my second point is 2, negative 3. Then I have 2 points, but now I also need to check those endpoints. So I need to check f of negative 1/2. So I need to substitute that back into my original equation and solve for the f of x. And when I do that, I end up with 1/8. So my next value I have is negative 1/2, 1/8. And then my last endpoint is f of 4. So I'm going to plug 4 in for x. And when I do that, I end up with 17. So when I look at all of those y values, I can see that 17 is the highest one. This is going to be my absolute maximum. And the lowest y value I have is the negative 3. So this is my absolute minimum. And if I were just to draw my graph, so this has to go up to, my max needs to be 17. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So 17 is going to be here, and 2, 4. So when x is 4, my y value is 17. This is my maximum value of my function on the interval negative 1/2 to 4. And when x is 2, I have a negative 3. This is my absolute minimum value. This is absolute max. This at 2, negative 3 is my absolute minimum. 0, 1, which is right about here. This looks like it could be just a local max and I have negative 1/2, 1/8, so that's really low. That's like really small right about here. That's going to be the endpoint on my interval. So you can see if I look at where I've graphed those points, the maximum is 4, 17, and the minimum is 2, negative 3 over there. All right, let's look at another example. I have this should be f of t equals 1 over t. And my first step is to take the derivative and set equal to 0. So I'm going to rewrite f of t as t to the minus 1. And then f prime of t equals negative t to the minus 2, which is negative 1 over t squared. So I've taken the derivative. The next step is to set it equal to 0. So 0 equals negative 1 over t squared. Well, this function is undefined. So this is undefined at t equals 0. But we'll notice that 0 is not in the interval we're given, right? Is not in 1, 2. So this has no relative extremum. But we can still evaluate the endpoints, right? So we're going to evaluate f of 1. So that's just going to be 1 over t, which is 1. and then f of 2, which is 1 over 2, which is 1/2. So we can see that at the endpoints we have our max, this is our max, and at 2, this is going to be our min. And actually, if I were to graph this function, 1 over t, 1 over x, kind of looks like that. And we're only looking at it from 1, on the interval from 1 to 2. And you can see that when f is 1, it's the maximum. And when f of 2, it's going to be, when t is 2, that's going to be our min. Our max is when t equals 1. Let's look at another example. I have f of x equals x minus 2 times the sine x on the interval 0 to 2 pi. So again, my first step is to take the derivative. So the derivative of x is 1, and the derivative of sine is cosine, so I end up with minus 2 cos x. And we want to set it equal to 0. So when I add, I'm going to add 2 cosine x, add 2 cosine x to both sides. And I end up with 2 cosine x equals 1. I want to solve for cosine of x, so I'm going to divide both sides by 2. So I want to know for what value of x does the cosine of x equal 1/2. And if I just were to draw the unit circle, you can see where that would be. So where does this equal 1/2? For what angle? Well, that angle is 60 degrees. So x equals pi over 3. But it's on 0 to 2 pi, so that also happens at this angle here, which is negative 60 degrees, or when x equals 5 pi over 3. So those are our two values. Our next step is to substitute those back into our original equation. So I'm going to find f of pi over 3. That's pi over 3 minus 2 times the sine of pi over 3, which is pi over 3 minus 2 times the sine of pi over 3 is the square root of 3 over 2. And this equals negative 0.68. Next, I want to find f of 5 pi over 3. So this is 5 pi over 3 minus 2 times the sine of 5 pi over 3, which is pi over 3 minus 2 times, and then the sine of 5 pi over 3 is negative square root of 3 over 2. So this is pi over 3 plus the square root of 3, which is approximately 6.97. And so I found the critical values, but I also need to check those endpoints. So f of 0 equals 0 minus 2 times the sine of 0. The sine of 0 is 0, so this is just 0. And then f of 2 pi, which is 2 pi minus 2 times the sine of 2 pi, which is 2 pi. The sine of 2 pi is 0, so this is just 2 pi. And this is approximately 6.28. So now when I look at these, I'm looking to find which one has the highest y value. Well, that's at 2 pi, this 6.28. So this is my absolute maximum at 2 pi 6.28. And then which one has the lowest y value, where that's at negative 0.68, which is here. So this is my absolute minimum at pi over 3 comma negative 0.68. So my those would be on the interval 0 to 2 pi. I have my absolute maximum at 2 pi 6.28 and my absolute minimum at pi over 3 comma negative 0.68. Okay, that's it for this section. I'll show you the practice problems in a document uploaded on Canvas.